Camilleri. He is, well, I first met him, an introduction through Gareth Davies regarding eVscopes. The society bought, this is the society's eVscope that we bought for outreach events. And I sort of get to have it at home for no good reason apart from I look after it. But I also do the citizen science that Michael's going to be talking about tonight. And Michael runs the New Zealand eVscope Facebook group.
I don't run it.
You don't run it. He's incredibly active on it and does an awful lot of work, and I'm sure he's going to talk to you a lot about that tonight. So, yeah, without further ado, we have a room full of potential budding citizen scientists waiting for you to talk, Michael.
Thank you. Thank you for this opportunity. I'll take you on a bit of a journey. It's going to be a bit of a personal journey to start with, and hopefully by the end of it there'll be some inspiration for you all. Once upon a time, I was a young man with an interest in astronomy. I actually went so far as to get a master's degree in astrophysics, but didn't progress that as part of my scientific career. So astronomy's been of an interest for a long time, but I never actually had a telescope of my own. So a couple of years ago during COVID, I decided to start small. So I bought myself a telescope, started to figure out how to actually do some observing for myself. And soon I encountered, I suppose, the first crisis of the urban astronomer, which is that with a small telescope from a light-polluted site, there's a limited amount that you can actually see. So after the first crisis, it was basically go big or go digital. And I didn't really have an appetite for aperture fever with larger and larger and bulkier scopes, so I decided to go digital. So that was just put a small colour CMOS camera onto that telescope, and I began my journey into electronically assisted astronomy. Some of you will have heard this term. It's kind of related to astrophotography, but it's basically astrophotography without all the messing around in post-processing. You see what you can see live or on the screen in maybe a few minutes. So you're using the camera to amplify what your eyes can see. And these are all shots that have been taken either from my front yard in Auckland or occasionally when I'm out on holiday. So this kept me entertained for quite a while actually, probably for about the best part of the year. And as you know, you go through the year, you see your various objects, and then they come around again. And at some point, you've got to find a reason why you're going to keep looking at these things. After a while, you know, one globular cluster looks much like another globular cluster. You need to find your why for why you're actually going to spend money on the gear and drag your ass out every night, especially in winter time. Now, for me, I don't have the time or the patience for astrophotography, so I was really looking for something else. So that's where the eVscope entered. So the eVscope was first produced a few years ago. It's the first widely available, fully electronic consumer level telescope. And along with that, Unistellar. So what I was wanting from that was easier setup and operation. Anyone who's run astrophotography, electronically assisted astronomy knows there's quite a lot of wires, as you can see, that you need to do. And I was also interested in citizen science, and Unistellar had an active citizen science program to go along with the eVscope. Now, for those of you who don't know much about the eVscope, it's a fully automated telescope. You connect it to it through an app on a phone or a tablet. And when you, it will align itself. It's got a database library where you just say, point to this object, it points to this object, finds it for you, and then you can press a button to actually record your exposure for basically as long as you want. So it's electronically assisted astronomy or basic astrophotography made easy. But what Unistellar has also done with this is they have built their own citizen science platform on top of it. So Unistellar partners with SETI Institute, also with some other space agencies and astronomy agencies around the world, and they offer the opportunity to do citizen science using the eVscope. So they offer, you can see here on the map, these are points where people have registered their eVscope, and most of the Facebook members are there. We probably have the highest proportion of Facebook members of eVscope owners of any country in the world, because we basically hunt them down and hassle them. It's one of the advantages of having Astrons as the sole distributor in New Zealand. We can kind of get to these people. So Unistellar has a worldwide network of observers. There's more than 10,000 eVscopes around the world now. Not everyone is active in citizen science, but potentially they could be. So they've got a very wide distribution. Unfortunately, it is mainly in the populated, light polluted areas. As you can see, there's not a lot in Africa, there's not a lot in South America, there's not a lot in Central and Southern Asia. So what Unistellar does is they curate events for citizen science. They have mission pages where on any given night you can look up for a particular type of mission, whether that be observing asteroids for planetary defence, looking for exoplanets, doing comet observations, or doing asteroid occultations, and the number of available programs continues to grow. So it's as easy as so the Unistellar scientists coordinate these observations. The observations are automatically uploaded. They do the analysis. They coordinate with the observers, and the Unistellar scientists will publish those results or file those results with the various organisations around the world. On any given night, so it's a very easy way to do science observations, because basically you just go to the mission page, press on a target. If it's one that's already loaded there, all the parameters are there, and you just keep an eye on things and file your report. So it's a very, very easy entry into doing science observations. And on most nights there'll be at least one observation possible, as long as you're not stuck on the inside of this ping pong ball that the Auckland sky has been for far, far too long. So this was a very easy and tempting way to get started. So I bought myself an eVscope and started to do some of these citizen science observations. Didn't really know what I was doing. Any of you who actually does do science observations knows that there's actually quite a lot to learn to do it for yourself. But this gives you a very easy entry, and also be able to do multiple different types of science observations, which otherwise would be specialties. So around about that time, I was doing these things by myself, discovered the eVscope Facebook group, got in contact with Gareth Davies, which most of you will know. He is a great asset to Auckland astronomy and a great asset to New Zealand astronomy. And he also has an eVscope. He's stuck on the side of Mount Eden, so he can't actually see much with it, but he does try. So I joined in March 2022, which is actually only about a year ago, so things have moved actually quite fast. And on the 4th of April last year, I very naively asked Gareth if he'd like to join me for an occultation observation, my first occultation observation. And I knew that if you could get multiple observers out, it was better. So I asked Gareth. I didn't know what I was doing. He certainly didn't know what he was doing, because he hadn't even tried, but we made the attempt. So we went for an observation of the asteroid TUCHKOVA. We were separated by about 5 kilometres. On the screen is the actual observation. And if you wait long enough, you might see the stars actually wink out, which is when the asteroid goes in front of us and completely blocks the light. So that will happen eventually. It did. Now, this was an interesting one because I didn't really have a clue what I was doing. I didn't know about the probabilities or the path widths or these kinds of things. But the line, we don't have a pointer, do we? That will be slightly helpful. Otherwise I'll just have to wave my hands and point vaguely.
It is, but it's one that plugs in. So. What you do is, you've got to hold it for a second and you'll get your pointer. There you go. So it shows on screen. So hold that one for a second.
Okay. So these were our 2 locations. We separated ourselves by about 6 or 7 kilometres across range, and this was the central line for the prediction. And this line down here, which I didn't know at the time when we committed to this observation, is the south side of the path, representing 1 standard deviation. The north side of the path is somewhere out here, and the limits for the observation are kind of, well, around here. So it actually turned out that there was less than a 5% chance that we were actually going to detect this thing. So when both of us caught it, it was really quite remarkable. So it did actually make a bit of a splash at Unistellar at the time, because it was one of the few times at the time when more than one observer had actually observed an occultation. So Unistellar then goes through and does their reports. These are the kind of reports they generate. They produce details of it. On the right-hand side there, this is a fit to the existing shape model where you can see the two chords that we got. And this helped to actually refine that model because they weren't sure whether it was left or right. That's one of the values of two observations. And it proved to be quite a useful observation. And it was great fun and very exciting at the time. So on the back of that success, we weren't quite so naive anymore. I had some idea what I was doing. So we reached out to Unistellar trying to get more people involved because the more scopes you can get out, the better. So we reached out to the local Astronomical Society. Gareth twisted quite a lot of arms and we got 8 new members on the eVscope Facebook page. Held a workshop to help people learn how to use the eVscope for science observations. And then we got 6 observers out for the next campaign, which was for the asteroid LINDELOF in May of 2022.
What did it use for timing? And could you perhaps explain what is actually happening here for people who may not know about an occultation? I don't know that many people here have attended one. The last one I did was in a farmer's field, and that was when we used WWF from Hawaii for timing.
Yeah, I'll get on to a bit about the timing. I'll just mention it a little bit. The timing's done internally. So with an occultation, what you're trying to do is you're trying to get the exact time for when the star disappears and reappears again. And from that time, you get a very, very precise position for astrometry. You need timing in the millisecond accuracy range, which is quite a challenge. The eVscope does it internally, does a reasonably accurate job, and it's good enough for most occultation work. I've got some timing gear here that will do it to the millisecond, and I'll talk a bit more about that later. So for this one, we got 6 people out, and 5 people missed. And the reason being was the asteroid didn't go anywhere near the predicted central path. It only went over the observer Wayne Humphreys, who was based down near Pirongia, and all of the others missed. So this is the advantage of having multiple observers, and we'd love to have more people going out for the same event because you have more chance of catching the object, and if you do get two or more observations, you get much more accurate astrometry. So the eVscope New Zealand Facebook page is still going, it's still quite active. Since then we have done some more campaigns, some have been successful, some haven't. Various members have had their observations published in papers, including a paper on Didymos in Nature, which is quite an achievement for Unistellar to get into there, also the Minor Planet Journal and some other journals. So it's a good place to do citizen science with the eVscope. Now, I'm just going to talk a bit about the DART mission because Unistellar had quite a lot to do with some of the lead up to the DART mission in particular, and I had some involvement in some of these observations. So, unless you've been living under a rock as an astronomer, hopefully none of you have been, the DART mission is a double asteroid redirection test. And this was an attempt by NASA to smash a spacecraft into the moon of an asteroid, not an asteroid itself, the moon of an asteroid, to see if they could alter its orbit. The idea with that is, well, nobody really had a clue what was going to happen. There were predictions all over the place for what would happen. No one really knows the characteristics of the objects or the momentum transfer. But the theory was, if you could crash a small spacecraft into an asteroid, you'd be able to deflect it. Do that soon enough before it gets to Earth, you might be able to deflect an asteroid without having to blow it up with a nuclear bomb or whatever that might be. So this is a very ambitious project. Now they needed accurate astrometry to know the position of the asteroid because they're trying to crash a spacecraft into it at about 25,000 kilometres an hour. The moon of the asteroid, which is dimorphous, was only actually about 170 metres across. So that's a very small target to hit, particularly when the initial position is not known that accurately. So occultations are by far the most accurate way of measuring the position of an asteroid within the solar system. And I do mean by far. I'll give you some more examples later. So what they were trying to do is find the position of Didymos, the main asteroid, which is about 780 metres across, which is quite small for an asteroid. It's a near-Earth asteroid. It was about 11 million kilometres away. So that's a very small object, a very, very long way away. The moon is smaller. It orbits Didymos, and the moon is about 140 to 170 metres across. So to try and get these observations, asteroid shadow hunters, occultationists, whatever you want to call them, from around the world, were coordinated by an organisation called AKHMEROV to try and catch this. And there's some information there if anyone wants to try and follow that up. So AKHMEROV goes after a lot of these near-Earth targets. So to do that, there were some initial predictions put out. The initial path was quite wide. The initial path would have been maybe 20, 30 kilometres across for an object about 780 metres across. So if you just plonked someone out there to try and catch it, you'd have very little chance. So Unistellar did one of the first attempts. They got about a dozen observers out in Dubai. They flew one of their people out there, collaborated with one of the local universities there. No one there had used an eVscope before. They showed people how to use it, got 12 people out in the field, and 11 out of 12 observations were actually a successful observation, but none of them was a positive detection. So despite going in the most probable place and spreading out over 5 or 6 kilometres with a gap that the asteroid shouldn't have been able to sneak through, they didn't manage to get it. However, it did help to narrow down the search. Then the baton got passed to Australia, where there are several bright star events. Now you need a bright star for Didymos because the duration is very short, and when you're doing very short, you're doing very short exposures, so you need a bright star to be able to enable this. There are a few events in Australia. Some people got out to try and do this one, including, I think it was John Brompton, who got set up 6 separate stations across one of the main highways, set them all up remotely, went away, and then came back and collected all of them up, and it took them basically all night to do it. Nobody got it. So that narrowed down the search a bit. And then eventually, this took a while, it was over several weeks, eventually we started to get some success. So anybody who's been in occultations for any length of time, or probably astronomy, has heard of Roger Venables. He's one of the true veterans of the sport of occultations, if you want to call it that. He managed to get the first detection in the USA. That was shortly followed up a few days later by a detection in Grenada. And the one for Grenada, that's the light curve there. So this is what happens. You're getting the light from the star. It's all over the place because you're doing very short exposures. You've got scintillation, and then suddenly the light flux drops as the asteroid goes in front. And this was only around about half a second, maybe, quite a short occultation. So that was the first light curve generated. Then we've got the major success in Japan. There's a very active group of occultationists in Japan as part of the JOIN collaboration. They got multiple detections on the 18th, and they got multiple detections on the 19th, and there was actually a probable detection of the moon, that object that's only 140 metres across. That's still a probable because that's a pretty hard one to get. So at the end of all that, these show the individual chords from the Japanese observations, showing that they've got different parts of the main body of Didymos, and that helps to constrain the shape. And that dot on the centre, is the barycenter of the asteroid. So that's where the centre of mass of that asteroid is. If you're doing photometry with a normal telescope, you get the photometric centre, the centre where the light is concentrated. So for a comet, that can be quite a long way from the barycenter. So that was all done. Then DART hit it, and it's disappeared off into the abyss because it's now too far away. Diffraction from such a small body means that the shadow is now too blurry and diffuse to be observed until it comes around again in about 2 years' time.
And hits us.
That one shouldn't hit us. So from all of that, there's a huge improvement in the orbit from these occultations results. The precision is down to milliarc seconds. That is like less than a milliarc second for the most recent observation. So I'll just try and find my pointer again. So what happened here, this graph here, these ellipses show the probable position of Didymos over a range of observations. So the blue one was before they started doing the occultations, and then as you get more and more occultations, you eventually get down to this little green circle, which was the combined results of those occultations, and that was when you got a position at less than milli-arc-second resolution. And you can see the scale here, this is kilometres. So they've nailed down the position to tens to hundreds of metres at a distance of 11 million kilometres at the time. It's quite remarkable the precision you can get from this. That was the occultation results. Unistellar was also involved in light curves of asteroids, where you can find things such as the rotational period of the body, and some of that information was also published. There were Unistellar observers on Reunion Island who caught the impact. They were the only people in the world to actually broadcast it or live stream it, and the Unistellar group was, I think, the only group that actually saw the reddening of the asteroid, because they were using colour cameras rather than mono cameras. So Unistellar has published a paper on their entire Didymos campaign there in Nature. So this gives you some idea of, I suppose, occultation at its best and its most accurate. It's a huge worldwide effort to get this. Now I'm going to get a little bit technical here. Some of you can switch off, some of you might switch on. Just talk about the accuracy of occultation and kind of why it works, give you a feel for what's going on. So when there's an occultation, you have a minor body, which could be an asteroid, a minor planet, a comet, goes between an observer and a distant star. Now stars are astronomically, pun intended, far away, so the light is essentially parallel. So the shadow that's cast on the Earth is the same size as the shadow of the minor body, and it might be angled because you're not perpendicular. So if you're off to one side here, the shadow will be at a bit of an angle and will be elongated. Now, occultations will routinely give an astrometric accuracy of between 1 and 5 milli-arc seconds using amateur telescopes from sort of 8 to 14 inch range. The Didymos observations, most of them gave an accuracy of about 1 milli-arc second, and the last one, partly because the asteroid was kind of at a point in the orbit where it was moving slowly relative to the Earth, it was a longer occultation, enabled greater precision, that was down to 0.1 milli-arc second. And that's tens of metres accuracy at 11 million kilometres. To give you some perspective, Hubble and JWST, their resolution is roughly, spatial resolution is roughly 50 milli-arc seconds. It's of that order, and that's similar to what the best large ground telescopes using adaptive optics, the sort of 5 to 10 metre class telescopes, will do. So the occultations are able to give very, very accurate positions, better than space telescopes can do. They're also not limited by atmospheric scene or disturbance. They're not limited by the diffraction limit of the telescope. The main limit is actually the signal to noise ratio. So brightness matters, the magnitude of the drop matters, your camera characteristics and sky noise to some extent matters. But as it turns out, these sort of 8 to 14 inch class telescopes are capable of doing this kind of precision on a wide range of asteroids for a wide range of events. This week on Thursday, there's like 20 events that I could potentially go after with my 9-inch scope. That would enable me to get this kind of accuracy if I do a good job on the measurement. Another thing is, you can see from this diagram here, the shadow size, it doesn't matter how far away it is. Whether it's a near-Earth object or out past Neptune as a trans-Neptunian object, the shadow size is going to be pretty much the same. So distance doesn't make any difference. And the dimmer, smaller asteroids are actually easier to observe than the large ones. There's an occultation of one Ceres, the first asteroid ever discovered, which has been known for a few hundred years. And that is quite bright. And occultations work best when the asteroid is dimmer than the star, because that gives you a drop in the magnitude. Ceres is at about roughly magnitude 8, so you need a very bright star for Ceres to go in front of it to actually get a drop. So the larger asteroids are actually harder to measure. So we've got this very nice thing going on where smaller asteroids are actually in some ways easier to measure and there's more events for them. So 5 kilometre size asteroids are routinely measured through occultations with moderate sized amateur telescopes to 1 to 5 milli-arc second precision. So it's it is true that a small amateur-sized telescope can give better astronomical position through occultations than Hubble or space telescopes can do using their normal photometry and astrometry. And this blows my mind, and it keeps blowing my mind, and it's one of the reasons I'm interested in occultations. It's one of the reasons that I do it. So, I've found my why. For me, I enjoy doing these occultation observations. I enjoy the hunt, I enjoy the thrill of the chase. They're short observations, you get a kick out of getting them when they turn up, and you're all done and dusted in a night, basically. So I decided to get deeper into these occultations. So rather than just using the eVscope, I decided to try and use my other telescope to do occultations. And this is where the fun really began, because the eVscope makes it really easy. You just follow a short tutorial on the website, you press a few buttons on the app. We have had people do their first occultation after they've been introduced on that day. We've had about a 90% success rate in people successfully performing the procedure the first time they do it. Now, I tried to get started and I needed help because it really was not easy. So there's a group called the Trans-Tasman Occultation Alliance. They're a section of the Royal Astronomical Society of New Zealand. I reached out and got some help from there, and a man, Dean Hooper, generously lent me some gear, some of which is here tonight, and that helped me to get started, because I was in a bit of a pickle. There's a lot of information to try to absorb when you're trying to get started here. So for the telescope, this is my current scope, but I started just with what I had, which was a C6 Schmidt-Cassegrain telescope. I eventually upgraded to a 9.25 because the 6 is really a little bit small for this kind of stuff. Aperture does rule. 8 inch is about the minimum for occultations. That can give you a pretty good setup, which is also portable. Fast focal ratio helps, not essential, but it does help in all sorts of ways. As far as the rest of the year goes, the go-to mount is very helpful. Doesn't matter whether it's Alt-AS or EQ mount. You don't need guiding. You don't have to have tracking. I wouldn't want to try an untracked observation myself, but people do these observations with an untracked Dobsonian telescope. So they're actually quite forgiving on equipment. You just need a reasonable aperture and a decent focal ratio. So that's kind of the easy bit. Then the real trick comes with occultations, because you have to have this accurate timing, particularly if you're going after smaller objects or trying to get a high accuracy. You need timing down to the milliseconds, and you can't get that off a standard computer. You can't get that really off a standard microprocessor. This does pretty well, but it's sort of on the margins. You actually need GPS equipment. So David was talking about using the worldwide radio service with the GPS time ticks. That service is now stopped in most parts of the world. That's how it used to be done. People would record audio, record video, or they'd be there with a notebook and listening for the pips. That's pretty much disappeared now. What tends to be done is using GPS for timing, because that can give microsecond timing accuracy through GPS units. So what's patients probably for about the last 15 to 20 years is to use analog cameras. This is a particular favourite, the Waytec 910HX. This is an analog security camera. For those young in the audience who don't know what analog is, it's these RCA jacks. There's nothing digital about this signal. This is old school television signal from the 1950s, and this has become rapidly obsolete. So you take the video through the camera, you thread it through a time stamper. This is a GPS puck. If we went in the basement of the building, it would be recording GPS position and time. And what this does is it puts a timestamp onto the video stream, which you can then put through yet another series of cables into your computer. So that's how a lot of this timing has been done for quite some time. The trouble we're having at the moment is that this is old technology and the availability is poor. So some of these units have been out of production for a while. That unit there, I managed to get off eBay. It was made in 2008, and that camera was borrowed. It was bought in 2012. There are some options starting to become available now. So that was one of the harder things, was getting started. You can use CMOS digital cameras. You have to use different timing methods, a GPS flash. which you can generate from a lot of different objects. You might even be able to set in there. No, it flash isn't going, but this actually flashes once per second once it's got a GPS signal on it. So this is what I've changed to doing now, using a modern digital CMOS camera, which has given me a lot more depth. It's more sensitive, gives me more occultations. So this is what my rig looked like before I upgraded and before I went fully digital. The scope, there's the GPS puck, there's the video camera plugged in, there's the cable coming out of there, there's the power supply, there's the control cable to adjust the camera parameters. That goes down into the box here, which has its own power supply. That feeds into this cable, which goes into here. And it's just a mess of cables and stuff everywhere. So it's a real sort of Rube Goldberg machine. And every time around it, you're sort of thinking, this thing's just going to fall over. It's going to break at some stage. And of course, with it being old technology, if anything breaks, it's like out with a soldering iron to try and fix it, or you might get stuck. So to do these observations, and this is true for all the different types of observations that you might do as a citizen science or a scientist, there's a whole set of observing process and protocols. There's various organisations around the world that deal with occultations. There'll be other organisations that deal with exoplanets and variable stars. They all have their process and protocols. There'll be a similar kind of thing going through. But this is what Unistellar basically takes care of for you. If you want to do it yourself, you have to go through all these steps from planning, setup, recording, analysis, reporting, publication, and so on. And you have to figure it out from yourself from the various guides that are available, which may or may not be complete or may not relate entirely to the equipment that you're using. So there's quite a learning process involved in here. There's a lot of software. Most of it's PC based, so if you're a Mac user, you're probably out of luck to some extent. This is the main software that I use. There's other stuff that I use. So at any given night, I'm probably using all of this to do an observation. So all of this has to be installed, configured. You have to learn how to use it. There's quite a learning curve attached to it. So this took me a couple of months to sort of get my head around to the point where I could actually reliably set up and do it. Before that, I had about a 50% failure rate where I'd mess something up and be late to target, or it wouldn't work, or something would go wrong. And then I started to hit my stride. So I'll just take you through what an observation on a night might look like. This is a real observation I've done recently. The asteroid AKHMEROV, I'm not sure if that's pronounced right or not. But I usually start with a program called Occult Watcher. And what this does is it lists potential asteroid occultations for my specific site. So it gives me a list of objects that I might want to go after. It gives me the information so I can decide whether it's within the capabilities of my system, whether it's one that I'll have the weather for or whatever. And in here, it also gives helpfully a little chart. This area is the predicted central shadow, and there's a couple of lines you can't see. For this, so this one was within the capabilities of my new scope, wouldn't have been within the capabilities of the eVscope. Viewing angle was favourable, and the probability to actually go across, for the shadow to go across my site was 14%, which is kind of higher than normal. Often it's like 5% or 3% or something like that. Occasionally you get a sitting duck at 100%, but they aren't actually that common. So I decided to go for this one. So when the night came, so you plan ahead of time, so you don't miss out. So on the night, this is actually where I observed from. It does look a bit darker than this, but there's plenty of stray light from surrounds the Te Peninsula, which is about a Bortle 5 area. Light pollution does matter, but it doesn't really affect occultation observations for the size of scope I had for the magnitudes I typically go after. If I was doing much deeper ones, it would be more important. So this is the kind of process I go through. I set up about 30 minutes before. Always important to check the event times because they're only, seconds or a half a second long. There's Occult Cloud is an online service which conveniently provides accurate coordinates, so I grab those from a go-to. Then that also provides a field of view, and then so the field of view of the star chart is on the left. This is what I had on screen to record. So with that you can check, and with a bit of practice, and believe me it takes a bit of practice, you can identify that I have the correct star here. That's a central star there, that's a central star there, and you've got this sort of line of bright stars here, this line of bright stars. So it's pretty convinced I had the right star. It can be quite hard to find because sometimes you're down to magnitude 13, 14, 15, and sometimes very dense star fields. And that can be a challenge for an amateur setup. It'd be a lot easier with an observatory setup, with a permanent setup and good star catalogues to work with. Once that's done, adjust the exposure, do a test recording. For this one, 80 milliseconds exposure was sufficient to get a decent signal. So that's me set up. If I'm set up early, I'm sitting there waiting for maybe 10 or 15 minutes. Occasionally you're late and scrambling and you just hit the button and hope that you're going to get it. So this is the actual recording from the night. So have a look, and did we get it? Oh, there it is, hit and hope. It's always hit and hope. Might help if you're a bit of a gambler in this game. So on the night, I was quite surprised, didn't really expect to get that one. It was a bit of a bonus. I thought I saw it, but then you actually have to do the analysis to confirm whether or not you do that. So this was done on the night. Sorry the colours don't come out that great. This is a light curve generated in Tangra, another one of those pieces of software, and you can see here that we have quite a nice dip, and it goes conveniently down to its estimated zero flux. This was just done quickly on the night to do a confirmation. Once you've done that, then, okay, that was fun. I observed an occultation. What am I going to do with it? You actually have to report it, otherwise, who cares? So there's another piece of software. I used AOTA, which is part of the Occult4 package. There's other ways to do it. This goes through and does statistical analysis and enables you to manipulate all sorts of parameters to try and get the best shape for the disappearance and reappearance, and calculates the times and adjusts the times for camera delay and all the kind of stuff that you have to do to actually get as accurate a time as possible. So this gave an estimated duration of 0.44 seconds. The drop is usually very quick. It's almost instantaneous, usually less than 1/100th of a second or even 1,000th of a second. It's usually a very, very quick drop. And this was, I believe, the first occultation ever for the asteroid AKHMEROV. So the next time round, we should have a much better position. Once you've got it, you fill in a report form and file it. In New Zealand, we do this through the Trans-Tasman Occultation Alliance, and they take care of sending the astrometry to the Minor Planet Centre. Light curves get uploaded and they get used to make further predictions, so the next time it comes around for someone, they have a much better chance of detecting it. So for this single observation, the barycenter was now accurate at the time of the observation to about plus or minus 3 kilometres at a distance of roughly 300 million kilometres, using a 9-inch telescope and a laptop in my backyard. So I've got time here for some discussions and questions on occultations. I will go and talk briefly about some other citizen science opportunities later, which I'm no expert on. So I just pause here so we can talk about something where I do actually know something about it. So you've got any questions? Yep.
How many milliseconds per image were you saying you're taking?
That was 80 milliseconds.
Okay, why not shorter? The signal to noise ratio.
Yeah, as you go shorter, the signal to noise ratio gets worse, and eventually it's not able to be analysed. You can go longer and you get a better signal to noise ratio. You can still recover the time, so it's not too critical. The main thing is that you can see the star and it's not bouncing around too much. Yeah, so the exposure times would vary between, I've done some at 10 milliseconds, I've done some at 300 milliseconds. It just depends on the target. But the main thing is if it's a short occultation like that one was 0.5 of a second, so it needed to be like 100 milliseconds or less, otherwise you just can't resolve the drop at all. So that's a challenge for these smaller asteroids. It's a shorter occultation, so you need a shorter exposure, which means you need a larger telescope, a more sensitive camera to be able to do it.
And you can adjust that with your web camera, the frame length, can you?
Yeah, you can adjust the exposure time on that in multipliers of 2. If you're using a digital camera, you can set an exact millisecond exposure that you want.
Why isn't the drop instantaneous?
Because there's diffraction around the asteroid, and the star itself has a size. So stars that are closer or larger, Betelgeuse being a very large and diffuse star that's quite close, those would have a slightly longer drop, but usually they're quite quick. Anything else?
It's obviously easier if you're mobile as well. Like if you've got a permanent observatory, you might have to wait once every 2 years for something that's going to happen over you.
No, not at all. It's if you've got an insensitive rig, a small telescope, an insensitive camera, which is basically where people were 10, 15, 20 years ago with the earlier cameras, then you did have to move. Also, 10 or 15 years ago, the predictions were not very accurate. So you'd make a prediction, they're only really predicting for major asteroids with major stars. Now that the Gaia Sky Catalogue has been released, which with roughly 1.8 billion stars in it, with very high accuracy, now that they've got the Minor Planet Center and Jet Propulsion Laboratory small body database maintaining accurate positions of asteroids, there are thousands of predictions being done every day. So for my telescope, as I said, on Thursday, there's about 20 potential opportunities. So it used to be you had to go to mobile to catch anything because the events were quite rare because they weren't predictions, they weren't very accurate. Is that I want some occultation buddies because I don't use that gear anymore. I've still got the loaner gear, so I've actually got 2 sets of analog gear that I could lend to someone and help them with. And I also know how to get people started up using a standard CMOS camera. So I'd really like to have some buddies somewhere in Auckland, particularly in sort of north-south direction, because most of the occultations sort of go east-west or west-east, and then we'd actually be able to nail a lot more of these multi-chord observations, which would be of much more value. So if you're interested, come and see me afterwards, over 6, 10, 12 per night. So you could use the eVscope, but there'll be a lot of days you won't have an occultation observation you can do, but of course you can then easily do the other observations. I can't easily do exoplanets or variable stars with my rig because I haven't set it up for it and I just don't know the techniques yet. So that's the advantage of the eVscope. It's the jack of all trades but master of none, I suppose. Any other questions? Yep, feel free to chat afterwards if you want to. Right, now I'm stepping away out of my comfort zone because I do some citizen science, but it's really only occultations that I have any particular knowledge about. What I'm trying to do here is just give an introduction to some of the citizen science activities that are available and just give you some encouragement to try and find something that you're interested in. So why bother with citizen science activities? Why would you want to make the effort? Well, there's some reasons. There's simply too much stuff out there for professional astronomers and large telescopes to look at. They need amateur observers to follow up and to keep an eye on a lot of these objects. And often they're not in the right time or place to be able to observe something. If you've got a network of thousands of observers around rather than dozens of professional telescopes, it's a big help. Amateur astronomers can help to fill this gap, and specifically for events like the Didymos Impact, for exoplanet transits for the James Webb Space Telescope. The TESS and other organisations actively want observations from amateur observers to go after targets of interest to either confirm or eliminate or refine parameters before they invest the incredibly valuable and incredibly expensive James Webb Space Telescope time. So you can actually directly support some of these space telescope missions and ground-based telescope missions. And of course, amateurs can do any crazy thing that they want to do. One of these citizen science crowdsourced ones, they took a look at brown dwarf stars, which nobody really knew what they were, and they found hundreds of them nearby that nobody had ever found. One of the early observations of the rings around Quaoar, which is a dwarf planet in the outer reaches of the solar system, that was one of the first detections was done by some Australian occultationists who just decided to record for 10 minutes before they normally would to try and catch it. And they found a ring system where it shouldn't have been, where the established physics, no one thought it was going to be. So there's some crazy stuff you can try simply because no one else will get funding for it, but you can do it. And of course, because it's interesting and challenging. So my challenge to you is find your why, find your reason. So I'm just going to run through some of the sort of options that you have, sort of from easiest to most difficult. The easiest and cheapest is the crowdsourced Zooniverse is a website that hosts a lot of these crowdsourced programs. You get to analyse real data from space telescopes and other scientific surveys. This is real science. They provide the online tools, they have the curated workflows, they provide the technical support, and it goes into real science with real publications and results. This is usually no cost. There's no equipment or software to install because it's all online. And it's a whole heap. I mentioned the brown dwarfs, that program's kind of winding up, but there's a huge amount known about nearby brown dwarf stars, which are basically too faint to be seen, even though they're quite close to us. Very active programs in exoplanet, galaxy classification. There's a weird asteroids program where some asteroids are doing some weird stuff. They're trying to figure out what's going on. Historical observations are quite a major area, also for New Zealand, and there's much more. So Zooniverse is one place to do that. You can also go to the NASA website, ESA website, and so on, and just find something that maybe you're interested in. Another cheap and fairly easy path is to actually take other people's observations and do the data analysis yourself. The main one I could find that does this is the NASA's Exoplanet Watch program, where you can check out a data set. They give you the FITS image files, they provide a tool that you can work with it, and you actually do the detailed analysis and then submit your results through that portal. Again, they provide technical support. There's little or no cost. You might need an AAVSO observer code. This one, you do need to learn how to use their more complex software and how to submit your observations. So still no cost. There's a little bit more effort and knowledge required on that one. So this would be a particularly good way to just, I suppose, try exoplanet observations and learn how they get done. METEORS, there's an active observation program. Fireballs Aotearoa, I'm not sure if anyone has heard about it. Hopefully you have. They're part of the global meteor network. They're out there trying to track meteorites so that then they can recover them soon after impact. This is modest cost. They're actually providing units, or just about ready to provide units to New Zealanders for about $550, and then you set up on the outside of your house. It all comes in one unit with a minimum of install. They have 50 sites already, and they're wanting more, and I've asked for one, so I should hopefully have one of these on my wall of my house sometime soon, and that might be the first and one of the early Auckland stations.
And you can do the data from there?
Yes.
Live?
So at Set and Forget, there's a web portal you can go and you can see your own data. If you want to do some analysis on it, you can, but that's more of a sort of Set and Forget type operation.
All sky cameras?
It's narrow field of view.
I think it's a 24 field, no. I'm not sure what the field of view is. It might be 80 by 40 degrees.
Quite a few in Auckland pointing in different directions.
No, from what I see, they actually want, in different parts of New Zealand, they're actually trying to catch them at about 100 kilometres height and then triangulate to try and find where they land. Anyway, you can go on the website and have a look, and then you'll soon know just as much as I do. There's also the CAMS program, which is a more sophisticated program. There is there's some sites around South Otago, but they're mainly concentrated to that area, so it's not really a New Zealand-wide program at the moment. Another low-cost option is to subscribe to a remote telescope where they can give you images on demand. Some of them also have the various scientific filters available, so they can give you science quality data just by you requesting it. So it's suitable for variable stars, exoplanets, asteroid light curves and comets. Not really suitable for occultations because from what I've found so far, none of them actually have accurate enough timing, and they probably wouldn't be happy about doing video at frame rates of 50 frames per second with the sort of file demands that would produce. These are telescopes worldwide, Australia and South America, two major places. So you can get sites anywhere you want and not have to suffer through all these cloudy nights, not have to stay up till 3 o'clock in the morning to get what you want. There's no setup cost, you just pay as you go. So this would enable you to focus on the analysis and not to have to worry about the gear. I have heard that there are some comet hunters in Australia that use small cameras, as in like camera lenses, to detect comets and detect asteroids, and then they do the follow-up observations by using one of these remote telescopes. So they don't have to invest thousands or tens of thousands of dollars of gear on their own large telescope. Then we get into the world of bring your own telescope, DIY observations, which naively I decided to step into myself. Here, the sky is the limit, pun intended. There's pretty much every type of science observation you could care to name. There's a lot of different organisations worldwide that will support amateurs in their efforts around here, and also support collaborations with professional scientists and scientist teams. Some of these observations you can do with camera lenses or small telescopes. There's some particular programs around variable stars that can use a DSLR or small cameras or small colour cameras, but in general you'd need something like an 8-inch scope or larger to be able to have a good range of targets that you could go after. For most of these you're going to need tracked. Some of them you need to do exposures sometimes minutes long, so you would need tracking and guiding. Occultations are probably the most forgiving because at such a short exposure, it doesn't matter if it's drifting all the way across your field and you're not after accurate photometry. These you need accurate photometry, you need darks, you need bias frames, you need flat frames, you need calibration stars. I heard some of you sort of talking about it. It sounds like I know what I'm talking about, but I don't. Because I have tried to start doing some variable star observations, but just haven't really managed to get far enough into it to actually get any viable observations left. So these are more complex. The gear's more complex, it requires more skill. The eVscope is capable of doing observations for most of these, and it trades off ease of use for performance. So there's fewer targets you can go after with an eVscope, but you can do things across all of these programs with a minimal of effort. And of course this costs time and money because you have to set up your own telescope to do it. The Royal Astronomical Society has a variety of sections which can give you local groups and support for many of these organisations. They have an historical section which I haven't really mentioned. They do all sorts of activities analysing historical observations, ethno-astronomy and so forth. There's a very active group there. Coordinated groups, occultations which I'm a part of, space weather, variable stars south, and there'll be some other organisations around. So there's plenty of opportunities locally where there can be locals to help you out. So the challenge to you is to find your why and to join the universe because we need you. Thank you.
Is SETI at home still going?
I don't know. That was using your computer to process data. I doubt it because of cloud computing, but I don't know.
So they still got that, I did it a couple of years ago. Go through slides and slides and try and sort of figure it out.
I'm not sure if there's an active one for that at the moment, but certainly people are still hunting for it because there's some hypothetical places it could be. It's just a very distant search. With the likes of the Vera Rubin Sky Survey and some of the other major sky surveys, they've probably got a better chance of catching Planet X than us astronomers, amateur astronomers.
Any other questions for Michael? Just, I mean, I put my hand up there. I was very lucky to get an observation on my first trial with the eVscope. I think I've failed every time since then. So that's partly the weather.
Yeah, I failed my first 17 observations. The ones that didn't just completely fail and got no recording. They were 17 negatives before I got my first positive.
Yeah, I was very, very lucky.
Now I'm on a bit of a roll. So yeah, it is a numbers game.
Yeah, it's pure skill, isn't it?
Absolutely not. It's incredible. I always set up very early at home, thinking, oh yeah, I might be able to see it from my deck because I have a good view out to the northeast and sort of there. Almost invariably, the eVscope, okay, you link to the particular observation, and the eVscope, once you've done your orientation, rotates around to the star you've got to be observing, and almost every time it's looking at my house. I've only got limited space where I can put my telescope, but it's always the house or the tree in the neighbour's. So it's fun and frustrating. So I've often thrown all the gear in the car, driven up to the East Coast Road, so I know I need to look that way for sure. So it can be a lot of fun. And the great thing about the eVscope is it's so fast to set up, and as Michael said, it's so easy to use. But the trade-off is, it can only do bright observations.
But it's obviously doing some pretty good science, though, isn't it?
Yeah, there's some good science being done with it. Unistellar's, I think, still hitting their stride on some of the programs. Because they have to figure out how to use this scope to actually give valid science observations. So there's some quite challenges in the background. Big advantage for Unistellar is the potential size of the network. So they have, they're actually a partner with NASA on their TESS, the Transiting Something Sky Survey, which goes after exoplanets. So they go after what they call targets of interest, where they've had some observation from the Sky Survey or the Space Telescope that says this might be an exoplanet, and it might have a period of 27 hours or 72 hours, or maybe there'll be a transit, you know, over this 3-day period. And of course, they don't have the space time to do that, so they give it to the Unistellar group, and the Unistellar's actually done one set of observations going worldwide, 27 hours of continuous observation of the same object, and that's pretty much only the Unistellar network can do that at this stage. So what they lack for and share, you know, aperture and observing power, they can make up for in time and spatial distribution of observers. So it's an intriguing proposition. So we just want to get more people more of those 10,000 people who have an eVscope actually doing science observations. So I think it's less than 10% are actually doing science observations at the moment. Yeah, most people are just going up, looking and saying, oh, that's pretty. Yeah. Go figure.
But and the great thing about occultation observations is that the negative result is as useful as the positive result. So seeing nothing is as useful as seeing something, because again it just limits the range of what the actual observation, the size of the object is. So it's really cool. Right, no more questions, and I'd ask you to please thank once again Michael for his fantastic work.